Southern Hemisphere, so it's very cool to be here. And today I would like to tell you about a modulated superconducting order that was recently observed in exfoliated thin flakes of iron superconductors. And I will first introduce some of the experimental results, and then I will present a possible mechanism for appearance of such an order. I have to begin by acknowledging my collaborators. So all the beautiful results that you will see in this talk were obtained by Ling Yuan, who works in Stefan's STM group at Caltech. And I also benefited from theoretical discussions with Patrick Lee. OK, so let me first introduce the two main components to understand the talk. So first of all, we already heard about iron superconductors in this workshop. And what I want to, particularly highlight that will be relevant to the rest of my talk is the crystalline structure of many of the iron superconductor materials. So the building block consists of a square lattice of iron atoms and also selenide or arsenide atoms that are both above and below this iron plane. So this means that the true unit cell of this material consists of two iron atoms. But because those materials are complex enough, and in many cases we can simplify the theoretical discussion to just working with the one iron unit cell, that's what many theorists assume, that we have no difference essentially between these two iron atoms. And the complexity of the materials arises from the fact that we have d orbitals. All 5 d orbitals can play a role in what is happening in the band structure close to the Fermi level of those materials. So this is exemplified when we look at an example band structure. So close to the Fermi level, we have multiple bands with complicated orbital texture. So dxz, dyz orbitals, dxy orbitals, they all play a role here. This is the reason why we often resort to unfolding of the 2 iron unit cell. So this is the Brillouin zone for the 2 iron unit cell into a 1 iron unit cell. But we have to technically remember that this would be the true unit cell of the crystal, and there are some cases, which will be important in this talk, in which we really have to work in the 2 iron unit cell. The important aspect is that, we have hole pockets around the gamma point, and around M point, we have electron pockets usually. That's what happens in those materials. So the other important part that is necessary to understand are the modulated superconducting orders. So this is, observing such orders is a long-sought goal, and we know that most superconductors have Cooper pairs with 0 center of mass momentum. So we have this Q equal to 0. We are pairing K and minus K, spin up and spin down, for example, and this will lead to a uniform in space order parameter. But already from the pioneering work of Fuldefer, Larkin, and Ovchinnikov, we know that there are circumstances under which we can actually have finite momentum pairing. And in this particular case, this was caused by introduction of external magnetic field, so which through Zeeman splitting led to splitting between the spin up and spin down Fermi surfaces, and we can no longer pair spin up and spin down states with exactly opposite momenta, but we will necessarily have this Q vector. And depending on the approach, you can either arrive at modulated amplitude, so our order parameter varies as a cosine Q dot R, or we can have modulated phase, so we can have this IQR, exponent of that behavior. So a natural question arises. Do we have to explicitly break time reversal symmetry to obtain such a finite momentum pairing? And this is a very intensively studied area, and the answer is we can have something called paired density wave, where through the strong correlations we can actually have a system in which the non-zero Q is the nature of the superconducting order parameter. Now, one important aspect that comes about during discussion of paired density waves is whether they are secondary or primary nature. So secondary means that we have a system with pre-existing charge density wave, and through this charge density wave, we then have this modulation in delta. But we are also very interested in finding materials in which this modulation in delta arises without anything happening in the normal state previously. So this is purely an superconducting instability. And such modulations were already observed in several different materials, in particular long wavelengths, so spanning over multiple unit cells, like for example here in cuprates we have like 8 unit cells. And after those results, we had multiple different material classes that exhibited this modulation of the superconducting gap. So we had iron superconductors, we had uranium telluride, and sometimes, well, the results can be seen in a bulk, and sometimes you need something particular like a domain wall in this iron telluride selenide on STO. So already observed in many cases. But the question is Q non-equal to 0 the only possible way to have something that, well, a superconducting gap that is modulated in space? And actually, well, the answer is kind of obviously no, because, well, if the modulation is commensurate with the unit cell, then, well, we have Q equal to 0, so we are not breaking the translational symmetry of the lattice, and we can still have the modulation. So in going back to our example of an iron superconductor, if we think about our 2 iron unit cell, and if we have a modulation that starts here, then, well, let's say we have a maximum here, then minimum here, and maximum here again. Well, this modulation would be commensurate, and it would be a Q equal to 0 order parameter. So I guess in order to slightly distinguish ourselves from the per density wave, which usually breaks the translational symmetry of the crystal, and, well, the Q vector is not really related, well, it's related to whatever particular Fermi surface you have, for example, in a given situation. So we would be calling this per density modulation. And, well, let me go to the experimental results that show that such a modulation is indeed possible and was observed. So the experiment is an STM experiment on thin flakes exfoliated from the bulk crystals of iron selenide telluride. So 0.55 telluride, tellurium, 0.45 selenium to be precise. So this is the combination that was also used in experiments that were looking for Majorana zero modes in vortices. And as you can see, the device, well, the flake is nowhere near single atomic layer. So those are, some people would call them bulk if they've seen that, well, the thinnest part is around 25 nanometers. But you can see that within this whole device, you can actually get areas of different thickness. So we can go from, let's say, 25 nanometers to 400 nanometers. And at the first glance, if you do your standard DIDV measurements, you can actually see a hard superconducting gap. And the magnitude of the gap is pretty much similar to what is observed in the bulk samples. And the same thing is true if you look at the temperature dependence. So the superconducting gap in the STM measurements disappears around 12 Kelvin. So this is the same as seen in the bulk samples, the same temperature dependence, which is slightly different than the transport gap, but I mean, that was also observed in the, well, so there's no transport data, I think, for those flakes, so this is only STM, but in the bulk crystals there was both transport and STM data, and there was a slight discrepancy between the TCs established for those methods. But what happens if we look more closely and scan across the surface? So first of all, I would like to highlight this topography image, and we see those bright spots. So those bright spots are actually positions of the selenium atoms on the surface. So this is what you can see in the topography. And since you can use them as a reference point, you can actually scan across the surface along the selenium atom direction. And what you can see is actually that there is a very nice modulation that can be seen. And if we want, well, we can extract the gap through the position of the coherence peaks. So this difference will establish the well, the gap in our case, and you can see that the data indeed shows a modulation. And this is quite unexpected because nothing like this was seen in the bulk crystals. And not only that, even in, well, flakes that are on the intermediate scale in the devices, so 210 nanometers, there's absolutely no oscillation. And the same thing for the bulk crystal before the exfoliation happened. So this is quite unexpected, and I don't think for this particular composition any modulation was observed before. So something definitely happened after the exfoliation process. And well, so I mentioned that well, the scan was along selenium-selenium direction, and after going back and forth with Ling Yuan, I convinced him to actually try looking at the iron-iron directions. And it turned out, well, even though it was quite difficult experimentally because, well, you don't have such a nice reference points for your scans, well, he was able to do that, and it paid off. So now you can clearly see a very large modulation. And moreover, the interesting thing is that if you determine what is the position of your, well, two iron sublattices, so this is very faint, but this is sublattice A, let's say this is sublattice B, sublattice A, B, the maxima and minima of the superconducting gap are actually pinned to those positions of those iron atoms. So we have a modulation that has maxima on one sublattice, minima on the other sublattice. And if we take a particular scan, so because this is again the scan, and I highlight that this is a distance of 1 nanometer. So we see multiple oscillations within 1 nanometer distance. And here is the example of CATS. So we can see that, well, we still have a hard gap, but we have a clear well, shift in the position of the coherence peaks. So again, reminding you the crystalline structure. So we have gap maxima here, gap minima here. But, well, so far, this is a one-dimensional cut. So, but, well, obviously, we have also different sublattices here. So we want to have a look at the two-dimensional structure. And indeed, when we look at a 2D scan in a, well, small area for many cases, but in this case, well, because the oscillation is so rapid on the unit cell scale, so this is a 5 by 5 nanometer area, and we can see that, well, there is some slow envelope of the gap changing, but on top of that, we have this rapid oscillation. And, well, you can extract this rapid oscillation and see that, indeed, you get a two-dimensional pattern. And you can correlate this with the topography image in the same area. And after you do some Fourier transform cleanup of the data, so, well, to make things more visible. So first of all, we look at the topography. So we have those bright spots, which are the selenium atoms, and those circles highlight those positions of selenium atoms in two different areas. And we can see that actually the gap maxima appear between those circles. So exactly where the iron positions are. So we have one sublattice has maximum and the other has minimum, because in one direction we will have one sublattice, in the other sublattice. There is also, I mean, there are domains, so there are regions in which this switches, actually. So what was gap maximum becomes a gap minimum. I mean, the sublattice that corresponds to gap maximum becomes sublattice with minimum, and vice versa. OK, so now we would like to understand what is behind all of this. So we need some additional input. Well, first of all, what changes in the exfoliation process? So one thing that can be noticed if measurement of the step heights is done. So it seems that the step height in the exfoliated flakes becomes much larger than what is happening in the bulk. So in the bulk, it's the C-axis in this material is around, let's say, 6 angstrom, but we have a distribution of step heights in the exfoliated flakes, and those are like 20% larger. So something is definitely happening after exfoliation. The other thing is when we look at quasi-particle interference, which we already heard discussed today. So we can have a look at the possible scattering processes. So normally, if we would have our gamma pocket and M pocket, we would see a scattering vector that corresponds to this distance, so this Q2 vector. But, and this is observed in other samples and I guess in the bulk as well. But in those exfoliated flakes, actually around the circle where the Q2 vector should be, well, there is nothing. So it seems like we don't have either gamma pocket or M pocket after the exfoliation. And well, in order to understand, well, which one is actually there and which disappears, what you can try to do, even though it's quite difficult, well, in those samples, but you can do a energy dependence of the QPI, and now you can see that, well, you have two shapes here which look like hole-like bands, so those inverted parabolas. So we can make an assumption at least, unless we will have a, yeah? Oh, well, this is just the Fourier transform of this, and what do you mean? Oh, well, yes, sorry. So the darker, the higher. Yeah. So this shape. I mean, I can also show that you can do a fit, and well, you can try to estimate that there may be two bands that are hole-like in here, and we also have an electron-like band slightly above the Fermi level, not exactly at the Fermi level, but so it's in the vicinity. Okay, so let's use this as an input for our model. So what we can do, we can also take into account that we are working with an STM measurement, so we are looking at the surface. So this, I mean, there are several aspects that can play a role in constructing this model, but so we certainly see that there is a difference between A and B sublattices. I mean, there is a clear difference in the gap. So there has to be something that breaks the equivalence between A and B sublattice. So one thing that establishes this equivalence between A and B sublattices is the glide mirror symmetry. So we can shift and flip our lattice and get the same thing as before. So it seems like, well, this glide symmetry is broken in this case. So I mean, if we are at the surface, then it's certainly the case because, well, obviously above the top selenium layer, we have vacuum. And, well, below the bottom selenium layer, we have the crystal. So this certainly breaks the glide mirror symmetry. But also the fact that, well, this exfoliation process certainly does something to the material in the, well, the C direction, let's say. Well, that gives another hint that there may be something happening here. So we construct a model based on the, well, 3D orbitals I mean, dxz, dyz, dxy orbitals around on the iron sublattices, all 3p orbitals on the selenium sublattice, but then we integrate out all the selenium orbitals to get just an effective model in the well, dxz, dyz orbital space, because we want to limit the number of parameters. But what we are assuming is that there is a breaking of this glide mirror symmetry, so that we can have well, difference between C1 and C2 in those two cases in this model. So we can get this model. We can have, well, multiple parameters because we allow for this additional symmetry breaking. What is important is, well, so we will have those two bands around the gamma point. We include, well, a band around M point to mimic what's seen in the QPI data. And the most important aspect is that when, well, one of those four parameters is not zero, so we have broken the glide mirror symmetry. And what appears is a sublattice texture. So normally we discuss orbital texture. So if we go around our Fermi surface, we have different orbital components corresponding to different states. But here I'm discussing sublattice texture. So some parts of the Fermi surface live on sublattice A, some parts of the Fermi surface live more on sublattice B. So this is the important effect of breaking of this glide mirror symmetry. We have this texture. So we have this first component that is necessary to get the modulation. Now, the second one is actually some anisotropy in the gap. So today we already heard about beautiful theories for nematic superconductivity that give highly anisotropic superconducting gaps. But what I'll do here, well, for the illustrative purposes, is something, I guess, more simple, more naive in a sense. So I will just consider the intraband and interband interactions of the BSES form with standard form factors for the, well, S component and D component. And if we, well, do in this case our self-consistent mean field calculation, we can get a phase diagram, and we can have those S and D order parameters. And depending on the, well, the interaction strength, so in general we have four parameters that describe interaction. So intraband, interband, and S and D channels. Obviously, we could have more of them to be precise, but this was enough, I guess, to illustrate what we have here. And well, on the right, we have the scale that, or the labels for the diagram. So we can have our pure S, pure D phases, but we can have S plus D in some cases when we have this interband interaction. So we have this region in which S plus D phase exists. So why is it important? So first of all, we can, well, start with the simplest possible S wave, which is momentum independent. So if we have our Fermi surface, then all the states on the Fermi surface feel the same superconducting order parameter. Now, if we would have our S plus minus case, well, if we had our M pocket here, then we would have opposite sign of the order parameter on the two pockets. So this is what is usually considered in such cases. And if we had a pure D order parameter, obviously we would have our nodal lines that cross the Fermi surface. So this means that we would observe a gap closing. But I remind you that we see actually a hard superconducting gap in this material. So if we have the mixed S plus D order, so now our nodal line looks like this. And if we put our Fermi surfaces on top of that, then we can see that, well, this part of the Fermi surface feels larger order parameter, this part feels weaker order parameter. And, well, obviously, this was considered, I mean, this appearance of those mixed S plus D orders was considered for iron superconductors. We can also have a different source of anisotropy like we heard today. The important aspect is that we should have some form of this gap anisotropy. That's what's important. So if we combine those things together, so this is our order parameter for the two Fermi surfaces, or two Fermi pockets, and this is the corresponding sublattice texture. Now, if our, well, anisotropy of the superconducting order parameter is aligned with the sublattice texture, this means that, for example, this part of the Fermi surface feels weaker superconducting order parameter. This part feels a stronger order parameter. So this means that, well, states on one sublattice will feel a different or stronger or weaker, depending on the situation, order parameter. And, well, the same analysis can be done for the other pocket. And if we now calculate our density of states in such a case, then we can see that indeed we get a different position of the coherence peaks. So we still have a U-shaped gap, but because, well, we are far away from the nodal lines in this particular set of parameters, but we have a clear separation between the position of the coherence peaks at sublattice A and at sublattice B. So in comparison with the experimental data, I mean, this is the major feature that could be reproduced. And they are fixed to sublattices, like in the experimental data, and the shift is comparable in theory and experiment. So if we look at a scan, I mean, compare what would the theoretical scan would be and the real scan, we can see that this quite resembles what we have in the experiment. Okay, now one more aspect here that we have is the temperature dependence of this phase. So if we have an S and D order parameters they do not necessarily have to appear at the same temperature. And well, we can see this in this mean field solution. So we see that, well, so we have 3 bands in the model, so that's why we have 3 curves, and the solid line is the S-order parameter, the dashed line is the D-order parameter. So for this particular set of, well, computational parameters, we see that at first we start to have an S-order parameter, then at some lower temperature, a D-order parameter appears. So if we plot how the density of states behaves at those points, B, C, D, E, then we can plot the density of states at the 2 iron sublattices at the different temperatures. So we can see that the important thing for the appearance of this modulation is that we have both S and D in this particular case. So we need to have the anisotropy in order to see the modulation between the sublattices. And here we can see that as we increase the temperature, so we decrease the D-order parameter more rapidly. At some point, so right after the D-order parameter disappears, we still see the, well, broadened superconducting gap, but there's no modulation there. So because we only have this S-order parameter. But as we, well, cool down or move up here, well, the larger the D-order parameter, so the larger the anisotropy, the larger the difference between the sublattices will be. Okay, so there is some experimental data, but only at a few different temperatures. So those are the scans at, well, 2.2, 4.2, 7, 9, and 15 Kelvin. And what one can do to analyze, well, what happens to the modulation is just, well, take the cuts of this data and do a Fourier transform and see if there is what happens to the Fourier component for this particular modulation. So we can see that, well, this modulation that would correspond to this, well, this per density modulation is largest at the lowest temperature, but as you increase the temperatures, at some point it seems to be vanishing. So, and this is and this is 9 Kelvin. As you remember, the superconducting gap disappears at around 12 Kelvin. So it seems like the transition temperature for the appearance of the modulation and for the well, so appearance of the modulation and appearance of the superconducting gap are separate. But, well, we would need more careful data in this particular case. So one thing that I wanted to mention is, well, the obvious problem of where the nematicity comes from. Is it existing in the normal state? What happens in general? And if we would have this normal state that is nematic above the superconducting transition, and we had this glide mirror symmetry breaking, I believe we would see a modulation between iron sublattices even in the normal state. Because, well, we would have, well, I can discuss this, after my talk, but I believe that would be the situation. So this would mean that we would already have some modulation in the normal state, and this superconducting modulation would be a secondary order. However, if the superconducting order is nematic on its own, then this per density modulation, so combination of the nematicity or the breaking of the or anisotropy of the order parameter and the sublattice texture would mean that this per density modulation is a primary thing. So as I said, there should be some modulation if the nematic state existed above the TC, and also I believe that this modulation would appear at the same time as the superconductivity appears. Whereas in the other case, if, well, we have the same charge density at both iron sublattices in the normal state, and also this modulation, well, if this theory is correct, then this modulation could appear at a different TC than the superconducting gap appears at. So evidence seems to point to this PDM, and there are other aspects that point to this being a primary order, but in any case, I mean, those exfoliated flakes are quite new. I mean, there are not that many experiments and characterization done on those, because apparently it's extremely difficult to prepare those samples so that they don't degrade, but we need more experiments. So to sum up, I hope that I convinced you that, well, those exfoliated flakes can actually exhibit exotic phenomena that are normally absent in the bulk. So we can look again at the thin flakes and see if there are some interesting changes happening. Well, I introduced this pair density modulation, which is modulated superconducting order, but with period equal to the unit cell of the crystal. So we are not breaking translational invariance. And well, I gave one possible explanation of the phenomena that are seen in the experiment for the combination of S and D order parameters. Thank you.
Questions? No. Okay. Okay. You are next.
Yeah, very nice. I have a question. You pointed out that in order to figure out if it's primary or secondary, you want to look for the same kind of modulation above TC or in the energies away from the gap. So couldn't you look for, because the iron, if you're looking on the selenium lattice, the irons are sitting in between, right?
Yeah.
And you have those two domains.
Yeah.
Now, there's a strong peak associated with this pi that's on the iron sublattice that shows up, and you saw it goes away at 9 Kelvin or so. But if there was a small modulation with different domains, you could still see it and say the Fourier transform of the actual selenium atom by comparing a QX and QY peak. Do you know, maybe this would be a question for Steven and those guys, but
right,
do you know if they looked at the anisotropy of the selenium Bragg peaks?
I don't think they observed anything on the selenium sublattice. So,
Okay.
so they looked at that because, well, we are exploring many. I mean, it was very surprising to see this modulation, and yeah, I don't think they've seen anything on the selenium sublattices. The difference between the two directions. Yeah.
Okay. All right. Thank you.
Yeah, thank you. Great story. A question on this related issue, namely whether the pair density modulation is the primary source. The reason is, I mean, what's wrong with the following picture? I have a D-wave superconductor that gets a little bit of beef to become an S plus D at some lower temperature, and then taken together with the broken glide symmetry, I would naturally get the modulation. I mean, I don't have to have an instability in that channel, or maybe I misunderstood something.
Oh, so my point is that you need to have an anisotropy of the order parameter. So I gave an example with this S plus D, but
Yeah.
if you would have something that gives you an anisotropic order parameter, which aligns with the sublattice texture, then you would get the modulation. So if you would have, well, what we heard about this morning, then yeah, this would give the same modulation. Yeah.
Okay, good.
So,
yeah.
I just wanted to say that, this doesn't assume that S plus D, again, just the anisotropy.
No, it's not a crazy thing to do.
Yeah.
I mean,
I know, but
you see the secondary gap in the density of states there, right? In your purple curve.
Yep.
Has this been seen in any of the data? Any shoulder?
Unfortunately, it's too broadened. So because this broadening here is not due to, let's say, well, finite temperature broadening or anything like that. It's just that different states feel a different gap in the anisotropic system. So that's why I'm fully honest, and I'm showing that, well, there is a tiny thing. And actually, this is interesting because if the experiment had enough resolution to see those things, we could actually say something about the relative sign of the order parameters on different pockets.
Right.
How they oscillate, whether they oscillate
That's
in
what I was
phase
asking.
or out of phase. So, but this requires, well, probably better samples. So this was hard enough to get those samples for the experimentalists. And, well, maybe trying to do this at even lower electron temperature.
Thank you so much.
Okay.
I wouldn't say clear. I wouldn't say clear. There is some evidence, but I would invite more experiments to prove or disprove whatever I'm saying here.
Why did you specifically choose the relative phase of these to just be S plus D and not?
So if we had S plus ID, in this case, I don't think we would see this modulation because we wouldn't see the absolute value at the 2 iron sublattices wouldn't be different. So yes, I know that there is S plus ID close by in energy. If we
But even with your diagram, once you break the inversion or the glide symmetry of the surface, I now have two inequivalent sites just by definition.
Right. But I think the important thing is the anisotropy of the order parameter and the sublattice texture. So yeah, yes, and also they have to be aligned. Because if I had a D that is rotated by 45 degrees, then I would see just 2 peaks at both sublattices instead of one sublattice, one peak, the other sublattice, another peak. So this may be also related to why it wasn't observed. So there has to be, well, stars have to be aligned to observe this phenomenon. And also, something is happening during exfoliation, and we actually don't understand what exactly is happening. We have some circumstantial evidence that, well, something happens in the Z direction, but that's it. So,
Just a clarifying question. So earlier, when you showed the experiment, there was a Q2 vector that was missing.
Yeah.
Maybe I missed the explanation. So the explanation in the end is related to this sublattice weight? Like, why is the Q2 missing?
Q2 means that, well, we either don't have a gamma pocket or we don't have an M pocket. So,
I see. So you're attributing to the lack of the actual pockets.
Right. And this was seen in some iron superconductors don't have either of those pockets, right?
The monolayers,
Yeah.
Okay.
So, but the thing is that from QPI you cannot say whether it's, well, because you are in Q space, as you explained during your lecture. Well, we don't know whether those are Hall pockets or electron pockets. So we don't know, without doing the energy scan, just from the QPI and the single energy, we don't know which pocket disappeared. So again, well, you've seen the whole shape of the band. Yeah.
Any more questions?
No. Actually, in the original story, we thought that it's the electron pockets that remain, but then, well, referees asked for additional data. Only then the energy-dependent thing was done, and well, then the story changed to Hall pockets, but it doesn't matter for this picture.
Okay. If there's any more questions, just a quick announcement before going to lunch. I have the list for the conference dinner. If anyone didn't sign, please let me know. And that's it. We'll start here at 2.